Hello guys, in this video I would like to share with you, we'll do something about variation of G with R. I would like to show you how can we relate the value of G, the value of G, where G is the gravitational acceleration with R, where R is the distance between center to center. Distance between center to center. So in our previous video, I had shown you how can we relate or how can we determine the value of G on the surface of any planet. Let's say this is our Earth, our lovely Earth. So the distance between the surface and the center, it is equivalent to the radius of Earth. So G, we could determine the value is equals to G m Earth over R square, or radius of Earth. And by using the same formula, we could also find the value of gravitational acceleration on any planet, any object, any stars, using G equals Gm over R square. So just make sure the mass is mass of the object and R is the radius of the object. So for today, today I would like to show you this one. This one where we can find or determine the value of gravitational acceleration, or gravitational force, or how can we relate the gravitational acceleration if the mass or if the object is placed at certain height from the surface. So that means now we are dealing with objects that position at certain height from surface of Earth. Before this, we assume that the object is exactly on the surface of Earth. But for today, this object is positioned at certain height from the surface of Earth. So what will happen? What will happen? So let's say this is our object. It has mass m, placed at height h from the surface. And then this is the center of the planet, let's say on Earth. So what will happen here? The distance between the center of Earth with the center of this object, now it is not equals to radius of the planet itself. So what we have here, the distance between these two objects will become, so this is the radius R, and this is the height, will become R Earth plus the height of the object measured from the surface of the planet. So this one, R Earth, if we are dealing with gravitational acceleration on the surface of Earth, or in general, we just use R equals to capital R plus H. So we will denote value of acceleration due to gravity at an altitude h meter. So h meter from the Earth's surface as g. So this one. Since you are familiar with this symbol G equals to the gravitational acceleration on Earth. So to make it easier for you, we will use G, G apostrophe here, as gravitational acceleration generally. So same thing what we had done before. Okay, same thing what we had been doing before. Okay, how can we relate this g, okay, g with the distance? So the distance now become r plus h, okay, r plus h. So this is the planet, this is the object, okay, mass m, and it is placed at height equals to h, and the radius of earth or radius of the planet, we just use any planet, so equals to r. So this object, although it is not on the surface of the planet, it's still influenced by the gravitational force of the planet itself. So that's mean, based on the Newton's second law, we can say that the object is influenced by the gravitational force of the planet. So the motion state of the planet is accelerating. So ma. So now we assume that the gravitational acceleration is equals to g apostrophe here. Okay, so g. So a equals to g. So what will happen to our equation here? F equals to m mg. Okay, where m is the mass, F is the force, and g is the gravitational acceleration at that point, at this position. And based on our Newton's law of universal gravitation, we have F equals to g m1 m2 sorry m1 m2 divided by r square. So although it is not at the surface of Earth, it still experience the force, the gravitational force, okay, due to the gravity of the planet. But of course, the magnitude of force will be weaker. Okay, will be weaker, since the distance here, become larger. Okay, remember, F gravitational force is inversely proportional to the square of radius. Okay, so the further we go away from the center of Earth, that's mean the magnitude of force will become weaker. So here we have F equals to G. M1 is the mass of planet. Okay, M2 is the mass of the object, and then so here we just put M, and this one M. Okay, this capital M, and divide by R square. So R, remember, R is the distance. So what happened to the distance now? If it is positioned or it is placed at certain height from the surface, now R become R plus H. And don't forget to square it. Now let's equate these two equations. So since this F that make this object, okay, this force which make this object accelerating downward is caused by the same sources of forces, or caused by the gravitational force due to the planet. So we can equate this equation, F equals to F, or F second law equals to F gravitational law. So F second law, it is mg. G is the gravitational acceleration. G m over m divided by r plus h square. So this is the mass of the same object. So what we have here is G equals to capital G, gravitational constant, times m divided by, so divide by r plus h square. Okay, now we have this equation. So let's conclude what we have here, or what we have, which equation do we have that we can use to find the gravitational acceleration? So we have two situations here. The first one, if the object is placed on the surface of Earth. Second situation, if the object is placed at certain height from the surface of Earth. So for the first situation, we can use G, okay, G equals to, so G M over R square, where M is the mass of the of the uh, of the planet, and then this one, same planet. Okay, so here we have G equals to G M over, so the distance now become R, okay, the radius of the planet, plus H square. So we have two different situations. Okay, this one near to the surface, okay, near to surface, and this one is at certain altitude, which is comparable to the radius of the planet. Okay, this one, if the height is very small, that means it is not comparable to the radius of Earth. So you can use either this one or this one. Later I will show you how can we use this equation in our calculation. So that's all, I think, and thank you.